Swayam Prabha. Digital India. Educated India.
Good morning to everyone. We are back into our lecture series on advanced hydraulics. We are going through the second module on uniform flows. In the last class, we had discussed on the aspects of design of channels for uniform flow. We have suggested that the uniform flow can be used in design of non-erodible channels, in the design of non-erodible channels, erodible channels. Of course, erodible channels we have suggested that it should not silt, and also the uniform flow can be used in the design of grass channels. So, in the last class actually we studied on the design aspects of non-erodible channels. What are the various factors that has to be considered while designing the non-erodible channels? We have suggested some of the concepts called hydraulically efficient channel section, other concepts called freeboard, how to provide freeboard and all, if you recall them. So, in today's lecture, what we are going to do is the topic will be same, it will be continued on the design of channels for uniform flow. So, this is part 2 of that. We will be discussing on the standard concept of standard line canal sections, especially in India. The Central Water Commission of India has suggested certain standard line canal sections. So, we will just briefly go through them. Also, we will have a brief description on design of erodible channels, of course, without silting process, and if time permits, we will go through the design of grass channels, or then if not, we will continue the same topic in the next lecture also. So, as we mentioned, today we will be going through the concept of standard lined canal sections. So, what do you mean by standard line canal sections? I hope most of you might have heard about Central Water Commission. The Central Water Commission, it is a part of Ministry of Water Resources in India. Ministry of Water Resources in India. So, this commission has many authority related to water aspects in our country. So, they have suggested certain guidelines, or they have suggested how to construct canals and all. There they suggested the concept called standard line canal sections. They use the standard trapezoidal lined section and the standard triangular lined sections. Like that, two types of standard lined canal sections they have suggested. According to them, the most of the channels should be of trapezoidal or the standard trapezoidal shape and standard triangular shape. What is meant by the standard line canal section? So, as we have mentioned earlier, the lined canal section means it is the non-erodible canal section. So, this standard line canal section, for whatever section be, there the corners are rounded off in your standard line canal section. So, for example, if it is a trapezoidal section, then you may see that the trapezoid, here the corner will be rounded off like this, and here it will be rounded off like this. Like this shape channels you may observe. If it is a triangular rather than like this, they devised it in the form of rounding it off and adopting the channel section like this. So, you can see such type of canal sections or the standard type standard canal sections in various parts of India. So, we will see what are the design aspects of the standard line canal sections. So, the standard canal sections, standard line canals, they follow certain geometry. So, they have a definite geometry, means they follow some rules of the geometry and it is been designed. The rounding of the corners, as we have seen here, the rounding of the corners and all. See the rounding of this portion, this is not done arbitrarily. They have a definite method, means how to round it off, from which portion it has to, the rounding off has to be started and all. They have a definite theory there and definite geometric principles are used. We will see for example, in the case of trapezoidal channel section, in the case of trapezoidal channel section, let me just draw the thing. It may be of like this. So, you have your bed. This trapezoidal channel section is having the side slopes 1:b, normal depth yn. Then the rounding off is started in such a way that from here at this location, if you just mark the straight lines with using the radius as the same depth as the normal depth, they will construct an arc that will perpendicularly bisect this portion. So, this is a perpendicular location and this is having the same length as yn, like this here. Now, this angle theta, now this theta is a design parameter. It is while designing the standard line trapezoidal sections and all, you have to identify what should be the theta value. Definitely for this portion, as you are aware, B0 is the bottom width of the trapezoidal channel. Side slopes are given as 1:b. So, with these quantities given to you, how will you design the standard trapezoidal section? So, for this you can now easily devise, means you can easily suggest that there are mainly 3 sections of area. One is the main rectangular area, let me give it as 1. Second, there are 2 sectorial areas, let me suggest this as 2, and there are another 2 triangular areas, let me mark this as 3. So, these 3 areas, they all come into picture when you compute the total area of flow section. So, when you compute the total area of flow section, you have to compute the individual areas of these figures or these shapes. So, for the sectorial area, there are 2 sectorial areas. I can give the area as twice into yn squared by 2 into theta. Fine. Theta is the angle, theta is the given angle. Now, let me ask you here, in this case, if the angle between the normal depth here and the radius given here that bisects the side slope perpendicularly, if this is theta, what will this angle be? Here also this angle. So, you know the property of means geometry property. So, this angle will also be same as theta. So, you can use the same concept here. So, when you compute the thing, sectional area, you know this is twice y n squared by 2 into theta. If you want, I can give it in the previous slide itself, so that you will not get confused. So, sectorial area twice into y n squared by 2 into theta. So, this is same as y n squared by, sorry, may I beg pardon, y n squared theta. What is the rectangular area? Your rectangular area, this is nothing but B naught into y n. So, these two areas now 1 and 2 are already available to you, that means it has been calculated. What about the triangular section, triangular portion of the section? There are two triangular portions given as 3, indicated as from one letter 3. So, you can compute them. Triangular area. For that, let me enlarge it for you for your benefit. If this was the side slope given to you, 1 is to B, and this is the portion where the radius of the curve that bisects perpendicularly with the side slope. So, at this location, so you have this quantity now. See, this angle is theta. Sorry, this angle is 90 degrees. This angle is theta, as we have seen through the geometry. This distance is y n. So, definitely, what is this height and what is this distance here? So, you can compute all of them. So, the triangular area, I can give this as half of, see, this is theta. So, y n by sin theta, that should give you this distance, right. So, half y into y n by sin theta into, then what is this height? This height is y n cos theta, right. Do I need to elaborate that? So, this is half times y n squared by tan theta. So, you can now relate theta with terms of side slope B, 1 is to B, that side slope, that also you will observe that your side slope whichever is given 1 is to B. In this case also, this angle is observed to be theta, or subsequently this angle will be theta. Therefore, 1 by B is equal to tan theta, or B is equal to 1 by tan theta. So, this relationship one can remember them, you can use them later on in subsequent cases and all. So, your total area A will, it can be written as B 0 y n plus theta times y n square plus y n squared by tan theta. That is, A is equal to y n times B 0 plus again y n times theta plus B. We have already shown you the relationship between theta and small b. What is the vetted perimeter of such a section? For the rectangular portion, you have the quantity B naught. For the sectors, you have the quantity twice y n theta. For the triangular portion, you can give this as y n by tan theta into 2. This is nothing but 2 y n into B. Therefore, your wetted perimeter P is equal to B 0 plus 2 y n theta plus B. Like this, one can find the wetted perimeter for the standard line trapezoidal section. Your hydraulic radius, this is nothing but A by P. It can be given as y n into B 0 plus y n times theta plus B divided by B 0 plus 2 times y n into theta plus B. So, the discharge using Manning's formula, that is 1 by n A r to the power of 2 by 3 S naught to the power of half. You want to design a standard line trapezoidal section. So, the discharge will be given to you. Based on that, one can compute the quantities here. So, what does this mean here? I can suggest this quantity as 1 by n B 0 plus y n into theta plus B, this whole quantity raised to 5 by 3 into y n to the power of 5 by 3 B 0 plus 2 y n theta plus B, this whole quantity raised to 2 by 3 S naught to the power of half. So, if discharge is given, you can now easily identify the section factor for the following channel section. For the standard line channel section, if q is equal to 1 by n A r to the power of 2 by 3 S naught to the power of half, then the product q n by S naught to the power of half is equal to A r to the power of 2 by 3 is called the section factor, right. So, if you recall this section factor, it can be non-dimensionalized. If you recall from our earlier lecture, recall non-dimensional section factor for trapezoidal sections. So, the non-dimensional section factor for trapezoidal section was based on the bottom width of the trapezoidal channel. This bottom width, based on this parameter, one has devised the non-dimensional quantity. So, this was given as A r to the power of 2 by 3 by B naught to the power of 8 by 3, or you can suggest that this is same equivalent to q times into n divided by S naught to the power of half B naught to the power of 8 by 3. So, what is the suggestion here? So, once you get the non-dimensional section factor for the corresponding channel, from you have already designed, if you recall that you had derived design curves, right, for non-dimensional section factor versus non-dimensional normal depth of flow. So, this process you do it again here, because this is now an entirely new type of channel, that is the standard line canal section. So, you again develop the design curve. How you do that? The non-dimensional section factor, I can give this as is equal to 1 by b naught to the power of 8 by 3 the whole quantity one plus y n by b naught into theta plus b, this whole quantity raised to 5 by 3 b naught to the power of 5 by 3 y n to the power of 5 by 3 1 plus twice y n by b naught theta into theta plus b, this whole quantity raised to 2 by 3 to b naught to the power of 2 by 3. So, this quantity just rearrange, cancel the terms appropriately, rearrange the things, you are now getting the terms in non-dimensional form. You see here, this is a non-dimensional parameter, this is a non-dimensional parameter. You will see here that b naught to the power of 5 by 3 is there in the numerator, it is there in the denominator, the whole quantity. This again can be rearranged. I will just show it in the next slide. Your non-dimensional section factor, it can be given as y n by b naught, this whole quantity raised to 5 by 3 into 1 plus y n by b naught theta plus b, this whole quantity raised to 5 by 3 1 plus twice y n by b naught theta plus b, the whole quantity raised to 2 by 3. Like this you will get your non-dimensional section factor. So, one can easily draw section factor by b naught to the power of 8 by 3, or I can write this quantity as a r to the power of 2 by 3, a r to the power of 2 by 3 by b naught to the power. This versus y n by b naught. You can easily now plot for the standard line trapezoidal section. Again here you will see that both theta and b simultaneously, there is no need for you to take it as parameter. If you know b, then you know what is meant by theta. If you know theta, then you know what is b. So, you can substitute, for example, theta, or if you recall that 1 by b is equal to tan theta. Therefore, theta is equal to tan inverse 1 by b. So, you can substitute wherever theta is coming into picture, this tan inverse 1 by b quantity. Similarly, if you want to use b theta instead of b, you can just do that. B is equal to 1 by tan theta. So, substitute this quantity now in the entire equation here, expression here, you will get your corresponding things, corresponding way you can obtain the parameters. So, you solve them, that is you now create the design curves. From the design curves you choose your appropriate non-dimensional depth of flow. Subsequently, what is the corresponding area of discharge and all can be easily identified. Okay. So, the similar concept now you can use it for standard line triangular section. So, I am not going to explain it too much here as is done for the trapezoidal section, but however, we will just briefly go through them. So, your standard line triangular section, it will be of the following form. So, curve, it will be rounded off by a curve. So, let me give this angle as theta, again this angle is theta, the depth of flow is y n, you know this radius will also be y n, this is same as done for the trapezoidal section, this angle will be your theta, because you know this portion is perpendicularly bisecting the side slope of the triangular section. So, therefore, you can give the quantities, geometric quantities like this, geometric parameters in this way, you can subsequently design the triangular section values and all, or you can find the corresponding section, what are the section dimensions and all. Where are the standard line triangular sections used? So, the CWC, Ministry of Water Resources India, they have suggested that triangular sections, standard line triangular sections have to be used wherever your discharge q is less than 55 meter cube per second. So, if it is less than 55 cumex, then you can use the standard line triangular section, that will be the better way compared to the excavating it in trapezoidal form and all. Of course, in trapezoidal form you will see that you cannot round it off properly, the corner may not be able to be round off using the geometry as mentioned earlier. So, you have to use their triangular section. That so, theoretically your standard line triangular section means, theoretically it means in the standard line trapezoidal section, if B naught is equal to 0, then that will give you the standard line triangular section. So, you cannot use the non-dimensional section factor as was devised for the standard line trapezoidal section, that cannot be used here. So, what is the wetted area of the flow in such a section? This is given as y n squared theta plus y n squared by tan theta, if you recall them. So, in the trapezoidal section there was a rectangular area also coming into picture B 0 into y n. So, that portion is not coming here, that is the only difference. So, your computation becomes much easier in that way. This is the area, your wetted perimeter P is equal to 2y y n into theta plus 2y y n into B 2 y n theta plus B. So, interestingly, what is your hydraulic radius? A by P, this is equal to, just compute it, I am getting this as y n by 2. Okay. So, now use these quantities, you can subsequently identify the discharge, means you just use the again Manning's equation, q is equal to 1 by n A r to the power of 2 by 3 s naught to the power of half you can identify section factor here q n q into n by s naught to the power of half. This will give you the section factor for standard triangular canal section. Okay. Section factor that is available here now. So, using the section factor now, you can easily incorporate the design parameters. Say here again you will see that a r to the power of 2 by 3 is nothing but equal to y n squared into theta plus b two by 3 this is equal to y n times 8 by 3 into theta plus b by the following numerical value 2 to the power of 2 by 3. So, you can employ this relationship directly, there is no need to non-dimensionalize the thing here, you will get section factor versus y n depth directly, because here again you know b is equal to 1 by tan theta or theta is equal to tan inverse 1 by b. You can use these two relationships, incorporate it here, you can identify which theta can be taken here, which b is better suitable here. Those things are available through your hydraulically efficient sections also. You can continue in that way. Next, before going into the design of erodible channels, just I want to briefly mention you wide channels. So, generally you may encounter very wide rivers, very wide channels and all. So, what do you mean by wide channels? So, if I have a following cross section of a channel. Now, this channel, such a type of cross section, it is generally considered wide channel. So, what is the quantity? How you can consider this wide as a wide channel? So, whatever be the shape of the cross section, suppose if you are able to approximate the hydraulic radius same as the normal depth of flow in any of the section, if you are able to approximate it like that, then that channel section is called a wide channel section. If you can check in for example, in rectangular section, in your rectangular section, consider any rectangular section, okay, you want the wide channel section, right. So, just redraw them here. A wide rectangular channel section, the depth of flow is y n, width of the channel is b 0. So, in the rectangular section, your area of cross section is equal to b naught y n, your wetted perimeter is equal to b naught plus 2 times y n. Therefore, your hydraulic radius r is equal to b naught y n by b naught plus 2 times y n. Now, in this case, if you closely observe for wide channels, the summation b plus 2 y n approximately same as your b 0 itself. this much wetted perimeter B0 length is there, even if you add 2 times the normal depth, it is not going to change the wetted perimeter that much. So, if that approximation is taken, your hydraulic radius becomes same as the normal depth of flow, or it is approximated as the normal depth of flow. So, if that criteria is there, then any channel can be considered as means if wherever the hydraulic radius is approximately same as your normal depth of flow, then those channels can be considered as wide channels. So, wherever in the questions and all, if wide channels are being clearly specified, you can take your hydraulic radius directly as the depth of flow, and the computations becomes much easier. Another thing is circular channels. In one of our beginning lectures, we suggested that if a cross section has a circular shape, then if the section is not fully filled with water, if it is only partially, if it is open to atmospheric pressure, the top surface of the water, then the flow in such type of channels can also be considered open channel, or the flow in such channels can also be considered as open channel flows. You can apply the theorems of open channel hydraulics in such cases. Say for example, here in this case, this is the top surface of the water in the closed circular channel. So, to design the circular channel, you can now suggest that, say, let this outer angle, let me consider it as twice into theta. Let me consider the outer angle as twice into theta. Your depth of flow is given as y n. Another property is the diameter of channel. This is given as d. It can be also considered twice into r naught. So, this dimension is r naught. Okay. So, here in this channel, your area of cross section involves area of sector. This I can mark it, this is 1, then area of triangle, this is given as 2. So, area of sector plus area of triangle. So, what is area of sector? So, as we have just gone through in the other standard line canal sections and all, this is now quite familiar for you. So, this is nothing but theta times r naught squared, right. Then what is the area of the triangular? So, what is the area of this particular triangle? So, this angle is 2 pi minus 2 theta. So, this is 2 pi minus 2 theta, this angle. You can use the geometric principles now. You can suggest that area is now is equal to, the area of triangle is equal to half times 2y r naught squared sin theta into cos theta. Do I need to explain it here? I hope you are able to understand. This angle is, the included angle is 2 pi minus 2 theta. You can divide, means you can make it into half. So, each of the half angles consist of pi minus theta, right. So, each of the half is pi minus theta. So, you know what will be this angle. This is, this distance will be definitely r naught by sin pi minus theta, and sin pi minus theta, what is that? What is sin pi minus theta? It is cos minus cos theta, or is it sin theta itself? So, you just tell me now. So, you will get the following form. So, this will be R naught, means this area of cross section, you will be computing it in the following form. So, this area I can give this as A is equal to R 0 squared by 2 twice theta on rearranging the terms, you will get it in the following form. The wetted perimeter of the circular section, this is nothing but twice R naught theta, this is equal to the diameter d given to you, d into theta. So, again one can use the same Manning's formula, 1 by n A r to the power of 2 by 3 s naught half. So, for designing the thing, you can take, means q is given to you based on the material n is available, channel slope based on the topography and the various criteria. If it is given, means if it is computed already. So, this term is taken and now you are going to compute the section factor. So, the section factor for the circular channel, here you can again think of the same thing, A is equal to R 0 squared by 2 twice theta plus sin 2 theta is given, P is equal to 2 R naught theta it is given. So, you compute it, compute R is equal to what? Based on that you devise the section factor. You can again form non-dimensional section factor here. If required, you can form the non-dimensional section factor, because you know the depth of flow y n, it is some function of the diameter of the section as well as the angle theta, right. So, based on that you can find the non-dimensional section factor appropriately, then you can design the thing. So, this is given as say q n, means the dimensional quantity will be q n R 0 theta whole to the power of 2 by 3 and this quantity to the power of 5 by 3. So, you can non-dimensionalize it using d, you can use the d appropriately and subsequently compute the design, obtain the design curves and subsequently design the circular channel sections. So, as mentioned, now we will just start the design of erodible channels. So, we have suggested that the erodible channels which we are going to take into account here is the channels that do not silt. So, if it is not silting, especially the erodible channels, they are very much complex, means you cannot, means we have to definitely take that the non silting property into account, then only the uniform flow approximation can be given for the erodible channels. Also, you require a stable section. Whenever you design a erodible channel based on the uniform flow approximations, you require some type of stable section. So, that also requires certain quantities. So, some of the methods used are method of permissible velocity, and method of attractive forces. So, for erodible channels, for designing of the erodible channels, these two methods are generally employed. What do you mean by maximum method of permissible velocity? We have suggested yesterday the method of minimum permissible velocity. Similarly, in the erodible channels, you require a maximum permissible velocity. There are various type of channels, you use different type of materials, whether if it is sand, whether if it is alluvial soil, whether it is clay, whether it is concrete, whatever be. Concrete, of course, if you know that it is non-erodible, means when you line the channel with concrete and all, it becomes a non-erodible. We are talking about the erodible channels. So, in that case, these gravels or whatever natural materials are available, for each of these materials, it may allow up to a maximum permissible velocity beyond which it cannot bear the force due to that flow. Until that portion it can bear the force and it will not erode. So, your maximum permeable velocity, it is called your maximum permissible velocity, it is called the greatest velocity. It is the greatest velocity that will not cause erosion. So, for different materials they have different maximum permeable velocities. Based on one's experience also, we have to judge which type of materials has to be used, or which what should be your permissible velocity and all. So, in this case, for example, a newly constructed gravel soil gravel channel may have less permissible velocity compared to an old gravel channel, because the old channel is already settled and you can have a higher mean velocity there, permissible velocity in design. So, the permissible velocity include, just for some of the materials, say for fine sand, you have approximately 0.45 meter per second. For fine gravel, you have approximately 0.76 meter per second as the maximum permissible velocity. For your coarse gravel, you have approximately 1.22 meter per second. Alluvial soils, you have approximately 0.61 meter per second. So, these are some of the guidelines, means some of the things already through various experiments and all, it has been designed. You can use them while designing the erodible channels using uniform flow approximations. What are the steps? The method for maximum, using the method using maximum permissible velocity. So, I can just number them. Say first you need to estimate roughness coefficient based on your material chosen. Then you have to estimate permissible velocity for that material, maximum permissible velocity. Then you need to compute hydraulic radius r. You have to compute hydraulic radius r from your Manning's equation. Say if V is equal to maximum permissible velocity and if this is a known value to you, from this relationship you can easily find your hydraulic radius r. The next step is you have to compute the water area required. What is the area of water or the cross sectional area of water that you need to compute it, because q is already given to you. Based on that, q by v is equal to a. Like this you can compute a, okay, the area of cross section. Once you compute area of cross section, then you know expressions for a and p. For example, in trapezoidal section, what is the expression for a, what is the expression for p, and all you know them. You use them. Identify for trapezoidal section, identify then what is your bottom width b and normal depth y n. You can use the design curves also here again, like that you can design the thing. Also, finally, you need to provide appropriate freeboard. Okay. Like this, you can use the method of maximum permissible velocity. Thank you.